Define it in different ways that other people can get. Like, actually, I don't know. I have to read this. So I'll read this and figure out how they're going to define it. They're just talking about silicon clusters and the stable silicon clusters and then weighing those and then defining it based on that. It's not so easy because silicon has two different isotopes, silicon 28, silicon 29. The abundance is varied. So not so easy. I don't know why they chose silicon. You know, maybe because of the cluster size or something. It forms a consistent cluster, but I'll look into it more, but it's pretty interesting. All right, so for redox, we have the chart method as an alternative. And so we don't need the single replacement. We could replace single replacement with the chart method. And chart method is just, you don't need any specialized knowledge for the chart method. All you need for the chart method is just to follow a series of steps. These are the steps. Just to review, inventory, find the strongest oxidizer, find the strongest reducer, combine the strongest oxidizer with the strongest reducer, making sure the electrons balance, and simplify. Determine the driving force, and you're done. So this is it. It's not so complex. So we did this one, copper and nitric acid, ages ago. We did this one, potassium. We didn't do this one, though. This one's a more advanced problem. This number 3 is going to require us to use the next method. The next method is skeleton redox. Did we do skeleton redox?
No.
Okay, so we got to do skeleton redox. Skeleton redox is a major part of chapter 19 of our book. And then this is more advanced. This is what we'll call the potential diagrams. What does the charge on manganese vary from? From what to what? Manganese goes from we don't want to complete the shell because for manganese to complete the shell, you know, it would need 1, 2, 3, 4, 5 more electrons to complete the D subshell, which would be -5, and then additional 6 electrons to complete this P. So it's not going to really gain electrons. Do metals gain electrons to form anions? No, metals tend to lose electrons. So metals are going to go from 0 to what? What's the maximum positive charge on manganese you'd expect? 0 to here, let's take a look at it. Probably need to look at the periodic table here. Manganese is going to go from 0, the metal, to plus. Well, if it loses its valence electrons, it's going to be plus. So this is D5. It's already half filled. It's going to be plus 2. But it could also lose these 5d electrons, which would bring it to plus 7. And so the charge on manganese varies from 0 to plus 7. These are called potential diagrams. So here we have manganese. What's the charge on manganese? Here we have manganese 2 plus, manganese 3 plus, MnO2, MnO4 2 minus, and finally MnO4 minus plus 7. And so what we have is we have this whole series here This one goes 0, 2, 3, 4, 5, 6, and 7. This is in basic solution. This is an acid solution here. Well, this is the redox chemistry of manganese. And these are the voltages, these potentials here. These we call reduction potentials. And we can use those reduction potentials to combine reduction oxidation potentials, combine with others. And then there's gaps. For example, we can go from +2 straight to +4, 1.23 volts, or +4 to +7. We aren't going to worry about the voltages at all. In fact, our book doesn't do anything with the voltages, so we aren't going to do anything with the voltages either. Okay, so that's the
skeleton method?
I'm sorry?
Was that the skeleton method?
No. That's called the potential diagram method. Potential diagram is much more. If you know, what we're doing is we're simplifying this. We aren't going to do potential diagrams. We're going to use the chart instead. And the chart is, if we look at manganese in the chart, what do we see manganese doing in the chart? We just see it going from plus, what's manganese here? Plus
7.
Going to, yeah, and so that's all. We don't see all the others, right? And so it turns out that, you know, redox chemistry, this is kind of the simplified version. If we were going to do it in more detail, we'd use a potential diagram to see what potential other products are going to form. But, you know, that's too much for us. What we want to know is just the basics, you know, how does it behave? And in fact, you know, most of the reactions you do, you take permanganate. Permanganate's a great oxidizer and acid, and it goes to manganese too. You know, most reactions. So these are the common ones. If you get familiar with this table, then you're way ahead of the game of that. But it gets more complicated. Not only you know, you can form multiple products or different products. You know, what dictates, you know, which of those manganese species you form? What dictates what manganese species you form are the conditions. You know, under certain conditions you form this, under other conditions you form that. Well, how do we predict that? Well, we could use a whole bunch of theory to try to predict it, but probably the easiest is just to mix it together and see what happens. You mix it together and see what happens. That's just purely experimental. We aren't predicting it. That's skeleton redox. Skeleton redox is just, forget it. I'm not going to try to predict it. I'm just going to try to mix it together and see what happens. Skeleton redox. So we have two different types of things we're doing in this particular chapter. One, we're trying to predict the products. And two, we just mix it, see what happens, and then clean it up afterwards. And so let's take a look at those two different types. So, you know, we'll just review chart method again, but I'm going to do a little bit more complicated problem maybe this time. Let's do silver metal plus HCl plus sodium nitrate.
So what would the wording for this problem be?
The wording for this problem would be silver plus hydrochloric acid plus sodium nitrate yields, sodium nitrate, I'd spell it out. Sodium nitrate
Yields. Like what was the question?
predict the products and driving force.
Okay.
So I'll tell you the common mistakes. Common mistakes. So people will write, rather than writing AGS solid, they'll write AG plus or even AG2 plus or something like that. That's totally wrong. Because I'm not talking about silver ion. I'm talking about silver, the element. Okay, then go to it. Let's see what you guys predict as a product. this is where having some familiarity with the charts can help you rapidly do this. You know, does this look like any pattern that you've seen, like double replacement? Maybe single, yeah, it does. It looks like double replacement here. HCl and sodium nitrate, right? It's like double replacement. But what about the silver? Well, let's forget about the silver right now. Let's just see, will a double replacement occur between these two? What would we form?
Would it be like sodium chloride and nitric acid?
Yeah, sodium chloride and nitric acid. So we're going from hydrochloric acid to nitric acid. If we go from hydrochloric acid to nitric acid, is that a driving force? Well, let's see. Let's take a look at the acid chart. Let's take a look at the acid chart. Where did I put the acid chart? We're wasting time again.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental.
That was when we did element plus element. Still have that video up. So that was this reaction.
Right.
Sodium and chlorine. That guy's this video was shot in Berkeley.
It's like,
So we're going from hydrochloric to nitric acid. Tell me,
we're going from a stronger acid to a weaker acid.
are we?
Yeah, because hydrochloric is stronger than nitric acid.
Does everybody agree? Everybody agrees that hydrochloric is a stronger acid than nitric acid? Hydrochloric is a stronger acid than nitric acid? Yes? Yes? No. No. Yes, it is. It is, but not in water. Not in water because of the, what do we call it? I use that, maybe it was a stupid analogy, but I use the picking the apples off the tree analogy.
Yeah.
Does anybody remember that?
Yes.
The lower apples are easier to pick than the higher ones. But, you know, if they're both within reach, then it doesn't matter because you're going to pick them all. So it doesn't matter. Can you tell, once they're in the basket, can you tell which apple was the lower one and which one was the higher one? No, because they're all going to be plucked off.
But even in the relative strength of acids in aqueous solution, hydrochloric acid is higher than nitric acid.
Yeah, so, okay, now we can talk a bit more because initially I just had you memorize it. But this is it. This is why I say, you know, when you guys review this, you can start making connections. One of the connections you can make is this. What do strong acids do in water? They ionize or they hydrolyze. To what extent do they ionize and hydrolyze strong acids in water? Do they partially ionize or partially hydrolyze, or do they completely ionize, completely hydrolyze? So let's take a look at this one. This is why I use this. Water has to pluck off the hydrogen here. Water has to pluck off the hydrogen here. So the hydrogen is the apple. Water is the picker. This is a Bronsted acid-base reaction. Which one is it going to be easier to pluck? It's going to be easier to pluck off HCl because it's stronger. And so what water is going to do is it's going to pretty much clean off all the hydrogens off the HCl molecules so that none of the HCl molecules have any more hydrogens left. They've been all plucked. They've been all plucked. And so what we've done is we've maximized the hydronium ion concentration in this. nitric acid is harder to pluck. And so this is like hydrochloric acid, I pluck it here. Nitric acid, I pluck it there. But what's water going to do? Is water going to have this more work, but will it be successful in plucking out? Yeah. It's going to clean off every single proton off there. And so what we end up with is this. We've completely plucked all the hydrogens off here. We've completely plucked all the hydrogens off here. So if we start off with 0.1 molar here, then we're going to end up with 0.1 molar here. If we start off with 0.1 molar here, so they're both equal in strength and number, are we going to see anything different here? No, we're going to get 0.1 molar here. 0.1 molar is pH 0. This is going to be pH 0. You know what this is? This is exact same pH. pH
0.
Can you tell the difference once the apples are in the basket, which one came from which acid? No, and so these are exactly the same strength in water, and therefore this is called the leveling effect because water is the picker here. And so this is like,
So are all acids the same strength in water?
all strong acids are the same strength in water. The weak acids, I used an analogy. The weaker the acid, the higher it is, and the more difficult it is to pick off the apple. So the stronger weak acids are a little closer, so you could jump. And I use the jumping analogy. So acetic acid, we can jump up and grab. Some of the other acids that are weaker than acetic acid, are going to be much harder to get. So we're going to pluck a lot fewer of those. If we pluck a lot fewer of those, then we aren't going to get as much hydronium in solution.
Why
And so,
does water want the extra hydrogen? Because isn't it pretty stable how it is?
yeah, there's no driving force for this. There's no, well, is there a driving? Actually, there is a driving force, because if HCl and water react, it forms hydronium, and we're going from stronger acid to weaker acid. And so this is why we say that HCl and nitric acid are strong electrolytes. Do you guys remember the electrolytes? Strong electrolytes completely ionize or completely hydrolyze. And so these are complete. Strong electrolytes are the strong acids, the strong bases, and the soluble salts. So those are all species that completely ionize. Then we have the weak electrolytes. The weak electrolytes partially ionize or partially hydrolyze in water. The weak acids and the weak bases partially ionize and partially hydrolyze in water. Then we have the non-electrolytes like sugar and alcohol. The non-electrolytes do neither of those.
Can we go over the difference between ionizing and hydrolyzing?
We could rewrite this one as this. This is called ionizing. It just breaks up into ions. Hydrolyzing is react with water. Hydrolyze means split water. Acids, we can represent either way, ionize or hydrolyze. Bases, we cannot represent either way. Bases only ionize or they only hydrolyze. So, I didn't really talk much about electrolytes, except when we're doing, remember when we were doing net ionic equations? Yeah. When we're doing the ionic equation, we only break apart the strong electrolytes, the strong acids, the strong bases, and the soluble salts. And the other ones we leave alone. But the leveling effect could have got you there. You gotta watch out. Leveling effect. And so there's no driving force for a metathesis reaction between these two, so we don't expect anything. no driving force, no reaction. So we've got to look for something else. What's the something else?
Wait, there's no driving force, but I thought that H3O plus was a weaker acid than hydrochloric acid.
Yeah, so a solution of HCl has what? A solution of HCl consists of H plus and Cl minus, and H plus is AKA H3O plus. I said that H plus, we use that as shorthand to represent H3O plus because it's just easier to write. H plus doesn't exist alone. Why? Does anybody remember why H plus doesn't exist alone?
Because it has to be.
It has to do with the size and the charge. Extremely high charge to size ratio. I don't know if anybody remembers that, but whenever you see H plus AQ, H plus AQ doesn't exist. It's H3O plus. But we still use H plus because it's a lot easier. But really, this hydrolyzes water. If it ionizes, then the H plus immediately reacts with water, forms H3O plus. So anyway, this will be metathesis review. If I take a beaker of HCl, what does a beaker of HCl consist of? It consists of H plus, aka H3O plus, and Cl minus. And then I'm going to take another beaker. The other beaker is NaNO3. What does a beaker of NaNO3 consist of? It consists of Na plus and NO3 minus. And then I mix them together. Which ions are going to combine? And so I have H plus, Cl minus, Na plus, and NO3 minus. Which ions will combine?
The H plus will go to the nitrate.
The H plus will go to the nitrate to precipitate out HNO3. So H plus and nitrate combine to form a precipitate, a gas, or a weaker acid. A weaker acid, they'll come together and stick.
They go to weaker acid.
A weak acid, I should say. And so, okay, they'll go to weak acid, HNO3? No, they won't, because HNO3 is a strong acid, and strong acids are completely ionized in water. There's no driving force because none of the ions are going to come together. Does nitrate love H plus? No, we talked about how bad all the chloride. I said, you know, I ran out of antacid, so I want to use table salt instead for an antacid. Will chloride neutralize my stomach acid?
No.
Why not? It's a base. So table salt
Because
will
it'll
work.
combine.
You know, how much is, well, milk and magnesia is kind of expensive. The Tums are kind of expensive. Table salt's cheap. I could buy a big 1 pound thing of table salt for 60 cents or something, less than $1. Just chug down the table salt instead of wasting $6 on antacid. Is it going to work?
No.
No, because all those bases are so weak.
That they're going to act as acids.
Yeah, and so nitrate's not going to have no interest in H plus, basically. This is why strong acid is a strong acid, right? And so do you see any metathesis happening? Metathesis is favorable. I don't see any metathesis happening, so this is why I said there's no reaction for the metathesis. AB plus CD. AB plus CD, there's no reaction. The other way you could have done it is we're going, what's the driving force? We're going from HCl to HNO3. Well, both of those are strong acids. And I know about the leveling effect. The leveling effect tells me all strong acids in water have the same strength. So you either memorize that or you remember it some other way. It's important for metathesis. Same thing with strong bases. So is there a single replacement between Ag and HCl? If you use single replacement method, there's no reaction between Ag and HCl because we're going from less active to more active. Is there a single replacement between Ag and NaONO3? No.
Why?
Because there's no dry. If you do single replacement, Ag plus NaNO3 yields what? Ag plus NaNO3 yields
That would be
AgNO3 and Na. Which one is a more active element? Sodium solid or silver? Which one's more reactive, silver or sodium metal? Sodium metal is much more. Do you guys remember Lake Lenoir in Washington? Do you remember what they dumped in Lake Lenoir, Washington?
Sodium nitrate.
No. That's sodium nitrate.
What are the directions of the activity on the periodic table?
I'm sorry?
Is there a direction, like the arrows for everything else? Or they're like, if you go this way and down, the elements get more reactive?
That's true.
It's left and down, right?
Yeah, but why? Well, actually, let me just explain it two ways. One, you wouldn't need a table for this because, one, what do they make coins out of? Silver metal or sodium metal?
Silver.
Why do they make it out of silver? Because silver lasts. Two, sodium occurs on the redox chart. What do you remember about sodium on the redox chart? What's the most powerful reducing agent on the chart? Lithium. Lithium and sodium in the same family?
Yes, they are. So it's very powerful reducing agent.
Yeah, and three, I showed the video on sodium metal being disposed in Lake Lenoir, Washington. That was sodium metal. If you dumped in 50-gallon jugs or 50-gallon drums of silver metal, would anything happen?
No.
That'd just sink to the bottom of the lake and we'd be a treasure. Last for a long time. Some treasure finder in the future could get it. And so there's no reaction here, but there is a reaction here. And so this is another failure of single replacement. This is the fourth failure of single replacement we're going to talk about. All right, we'll talk about this next time then, so we're out of time.